All right, so now we are going to pick back up at the optimization. And so last time we just did some review of some mathematics that's relevant in different ways in optimization. And some of it we're going to use more directly and some of it less directly. And it was more just helpful at reminding us of things that might occur maybe in the optimization literature that we might not use so much. Like, for example, the directional derivatives, those are used in a proof that we're not going to discuss. But then it does still help you think about directions in multidimensional space, which is a concept that we'll use, and then also gradients for sure, and things like this. And so what we'll do now is pick up where we left off. So we are looking at the fundamentals of unconstrained optimization. And so there are some things to think about here. And so this is firstly that we want to be able to write out conditions that signify different things about local minimizers. So the idea with a local minimizer is essentially that it gives you the lowest value of your objective function among nearby points. And so there are going to be necessary conditions related to optimality, and there's also going to be sufficient conditions. And so necessary ones are going to be ones that assume X star is a local minimizer, and then tell us things about the gradient of f at the optimal point and potentially the second derivative matrix or Hessian as well at that optimal point. So first we're going to have here the first order necessary conditions. So what these say is they say that if X star is a local minimizer and f is continuously differentiable, in an open neighborhood of X star, then gradient f of X star is equal to 0, meaning that it's equal to the 0 vector, because the gradient is going to be a vector. And so note that differentiability here is with respect to your decision variables. And if you're wondering, like, okay, how do proofs go in optimization? We're going to do a few to start to give some feeling of some of the ways people do proofs in optimization. And we're clearly not going to be able to cover a lot of what's out there in essentially like 2 lectures on optimization or whatever. But we're going to go through this proof really quick. So this is a proof by contradiction. And so it starts by saying, suppose that the del f of X star is not 0, but X star is still a local minimizer, and f is still continuously differentiable in an open neighborhood of X star. So you can see that this is the opposite. So this says if it's a local minimizer and f is continuously differentiable in the open neighborhood, then this gradient of f at the local minimizer is equal to 0. And so this is saying like, okay, well, let's say that that wasn't true. So say that it is a local minimizer, that it is continuously differentiable in the open neighborhood of X star, but that del f of X star is not 0. Then what would happen? And so what we want when we do proof by contradiction is we want to show that the thing that would happen is impossible. So then we say, okay, well, if it couldn't be this way, since it has to be something, if it couldn't be 0, or if it is impossible that it is not 0, but it has to take some number, then it must be equal to 0. So in order to look at this more, we're going to say, okay, I'm going to define the following thing. We're going to take a vector, p, and we're going to set it equal to negative del f of X star. And we say, okay, this is just by definition. So right now, since del f of X star is not 0, this would be p does not equal 0, because the del f of X star is not 0. So then we can write this and say, okay, what would this be? The dot product of p and del f of X star, or p transpose del f of X star, which now we're used to are the same thing. So then this is going to equal, if this is my p, this is going to be negative del f of X star, and then transpose here, del f of X star. So we know from things that we've done before that if we have X transpose X, this is the same as writing here like the 2 norm of X squared. And so what this is going to give us is this is going to give us the negative. I'm just going to write the 2 norm right here with no symbol here, but let me say this denotes the 2 norm. Now, if you have a norm, because the norm has to meet the properties that we've already talked about for norms, the requirement is that if you take the norm of an argument, that it needs to be greater than 0, and 0 only if the argument is 0. So if we're saying, okay, this does not equal 0, then by definition, this has to always be less than 0 strictly. So because this is not 0, that means that the norm has got to be greater than 0, so the negative of it is going to be negative. So this is strictly negative in this case, under our assumption that this thing cannot be 0. So then we want to make an argument about continuity. So del f is continuous near X star, which we know because of these types of statements. So since it's continuous near X star, what we know from that is that it's not going to be able to go immediately from having like that this would be like that this would not be 0 to then suddenly now it's 0. Like since this is not 0 and this function is continuous near the optimal point, it must be true that this remains not 0 for at least some number of additional points. And so then we can say, okay, well, that means that for a very small neighborhood around X star, I can still do this P transpose del F of X star plus some small amount, so offset this vector a little bit from X star, and this should still be negative because like we were saying, I'm not going to drastically change the value of del F of X star to make it now suddenly equal 0. So this is going to remain that when I do the P transpose del f of x star slightly offset, this is still going to be negative. And so this means that there exists a scalar t that's greater than 0 such that P transpose del f of x star plus TP is negative for all t in 0 to t, where this is the uppercase T. And so what this says is this is really an expression of continuity, that if I offset my x star here by just a little bit, I'm not going to suddenly change this other function from having been negative with x star to suddenly being positive with only a small t and being added over here. And so we can see this as a direction P, that we're sort of having this scalar say how far down that direction that we're going. And so now what we write is we write that for any t bar in 0 to t, then Taylor's theorem says and we would get that f of x star plus t bar p equals f of x star plus t bar p transpose del f of x star plus tp. And so therefore, this would give me that this is less than f of x star. And so you might say, oh, how do I know that? Well, because we just said that this part is still negative. And so this would have to be true for all t bar contained in 0 to t, which is the range where this remains true, so that this would be true. And so what this would mean is that there exists a direction, this p direction here, leading away from x star where f of x star plus t bar p is less than f of x star in that direction. And so this is a problem, right? Because we said that f of x star should be our minimum. So how is there a direction where even if we just go a small amount in that direction, just even the t bar is between the 0 and the t, that now already I'm getting that a point in that direction is less, or has an objective function value that's less than the objective function value at the optimal point. And so the problem with this is that then that implies that f of x star is not optimal, or it is not a local min, or a local minimizer, because you can do better with your objective function than you can at x star by just changing where you're at by a slight amount away from x star. So this is not a local minimizer, and so that's a contradiction. So del f of x star can either be 0 or not 0. When it's not 0, then x star is not actually a local minimizer, so we get a contradiction with our assumption. And so therefore it must be true that del f of x star equals 0 is going to be the case that that x star, that happens when x star is a local minimizer. Okay, so that gives some idea about how proofs kind of go in some of this early stuff for unconstrained optimization, is that there's some statement, and then you can make some proof by contradiction that involves Taylor's theorem and things like that, can help you with proving some of the things. And so now I'm going to write the second order necessary conditions. So these first ones that I had here, first order necessary conditions, the reason these are first order is they're about first derivatives. As you can see, only the gradient vector is involved here. So now we're going to have second order necessary conditions. And so in this case, we're going to have that if x star is a local minimizer of f and del squared f exists and is continuous in an open neighborhood of x star, then del f of x star equals 0 and del squared f of x star is positive semi-definite. So what the way you would then go about proving this, I would encourage you to go give it a try. You will do something to use the definition of positive semi-definiteness, and then also try to prove by contradiction again and see how far you can get on that. And so those are some order necessary conditions. There's also what we call some sufficient conditions. So what the idea with a sufficient condition is that you don't have what you have up here. So here for the necessary conditions, we say assume x star is a local minimizer, then the following things are true about del f of x star and about del squared f of x star. With the sufficient conditions, it's going to go the other way. So it's going to be given certain things are true, about the derivatives of f, you need to guarantee x star is a local minimizer. And so the idea for necessary and sufficient, the way that you would think of it is like it's necessary for x star to be a local minimizer or sufficient for x star to be a local minimizer. And so there's that like if x star is a local minimizer, then these things are just a necessary condition. If it's a local minimizer, then it is necessary that also del f x star and del squared f x star satisfy certain requirements. And this one is sufficient because it says, okay, if certain things are true, then this is a local minimizer. It doesn't necessarily mean that those things are true, that x star cannot be a local minimizer. So it is sufficient, doesn't hold that x star is a local minimizer, but it's not necessary in the sense that x will be a local minimizer without the other things holding. So that's the idea of necessary and sufficient. And so you could again try to prove on yourself as well, but here's the second order sufficient conditions. And these say that you suppose del squared f is continuous in an open neighborhood of x star, and that del f of x star equals 0 and del squared f of x is positive definite. Then x star is a strict local minimizer of f. And so let's look at the local minimizer. So x star is a strict local minimizer or a strong, just say local minimizer, if there is a neighborhood n of x star such that f of x star is less than f of x, from x in the neighborhood when x is not x star. So the idea for this is that it's not an inequality. So if it was f of x star is less than or equal to f of x, then it's not a strict local minimizer. Instead, notice this makes a stronger requirement that f of x star has to be strictly less than f of x. And so this is then a sufficient condition. So if del squared f is continuous on the interval x star and del f of x 0 and del squared of x is positive definite, then x star is strict local minimizer. But you could have x star as a strict local minimizer and it doesn't matter. So that's why it's sufficient and not necessary. Like I suggest putting this one to result of trying to get it go. Okay, so there are certain things that are nice, like when you have a convex function, any local minimizer is also a global minimizer like this. But let's move on to the point to discuss things about algorithms for unconstrained optimization. So we are going to very specifically consider the case of smooth functions. So it's going to be algorithms for unconstrained optimization of smooth functions. So the idea for all these algorithms is that for the most part they start with s of x0, and then they generate sequence of iterates. For the decision variables would be say x k k equals 0 to infinity. The idea of this is that you try some initial s x0 decision variables, then the update your guess into x1, see how that does, and tries it now x2, etc., etc. And you stop generating, restart these, stop generating new iterates, and some mission traces net. So that can something like that. Not making progress anymore, so it seems like you're not making big updates to x anymore, or or it could be other things as well. And so the goal of this is to make it so that new layers decrease your objective function f. So you want f at x k plus 1 be less than f of x k. This is what you want. So you say, how do I get there? So how do I choose these points as one such as the relationship to x k? Well, then for this, there are techniques called line search and trust region. So the basic idea of these is the following. So for the line search, the idea is that you want to choose a direction, pk, and they want to find how far to move this direction. So they say u, I mean the decision variable vector. So ideally what you want to do, you want to say, okay, I want the minimum value of my objective function evaluated at xk plus alpha pk. So this is the idea that you have, you take your initial point, and then you have some direction here, and the, you have some like step length here. So the step length is this alpha, and k is the direction. So you say, okay, if I try to move alpha length along the direction pk, then ideally you would find the alpha that causes you to multiply this versus pk divided by. So often we don't solve this in exactly in practice, but you get an idea of what you're going for. So then the next part is the trust. So the trust region will be different. So it will start by saying, like, suppose that you try to guess or to approximate the equilibrium function. That might be something like your m divides like the model that it's using of the objective function. So it would be equal to the objective function of iteration k plus p transpose del f k plus 1/2 p transpose bk p. And so here this is like a second order approximation via Taylor series of your objective function. The objective function has to be sufficiently smooth that take a second approximation of the Hessian or a derivative matrix. So that's just so similar to the and so then what you want to do is you want to say, okay, I want to solve this problem. I want to find a direction that makes my model at k plus p. Sorry, this on subject. You want to find the p so that you try to get this approximation of your objective function as small as possible in the direction of the p that you're choosing. And so you can't just choose any p. You have to choose a p in the trust region. And so what the trust region is generally something like the norm of p, like the norm must be less equal to some verb. And the idea is that this is your trust region radius. And what the trust region is, like what are you trusting? What you're saying is that this approximation of the model of the objective function, which is essentially accurate, maybe in a neighborhood of the origin, as long as your objective function is sufficiently smooth, it would be like in a neighborhood of the origin that you would, or not of the origin, in the neighborhood of xk, that you would be able to get this approximation to approximately be the objective function value. And then so if that's a small enough neighborhood, then your trust region has to be sufficiently small, and you're only looking for steps within the trust region sort of radius. And so we can give a little bit of the example of the idea. I'm going to save that for next time.